Karina Ulchigrai, thank you, from Bristol, about dynamics, polygonal billiards, and periodic surfaces.
Okay, so thanks a lot. So thanks a lot for the invitation to Beatrice. I'm glad to be here, and I'll start, as you know, by telling you something about my life and my career. So I was born in Italy, in Trieste. That's me when I was in primary school, I think in first grade. The little picture in the corner. I don't know if I have a pointer. And yeah, so I started liking mathematics probably because I participated in the mathematical Olympiads, and I kind of liked the problem-solving aspect. And then I decided to try the exam to enter Scuola Normale Superiore, that's in Pisa, in Italy. And I got a fellowship to get in, so that was great. That's where I studied, and I did my undergraduate studies. And that's all of a sudden I found that I was the only woman, but that was not a problem. But there were all these very intelligent guys, and I felt like I think I learned today from Nalini, I gave a name to what I had. I think I had the imposter syndrome. So I was saying, what am I doing here? How did I get in? Will I ever be able to make it? And in reality, I did very well, but I think I lived very badly because I didn't have this self-confidence to understand it. So yeah, so if you have the imposter syndrome, do try to cure it because it just makes your life bad. And I think it's not a female thing, but I think it's definitely more frequent among women mathematicians than men. So yeah, and then almost randomly, I actually applied to go abroad, and I got admitted at Princeton. And I think the imposter syndrome continued because at that point I was kind of trying to think, oh, will I ever be able to prove anything? Will I ever finish my PhD thesis? And I guess that's something which is, again, very common for every graduate student to kind of wonder whether. But again, well, I think I did well, but I just lived badly during those years. But no. So, and yeah, actually just after one other year that I spent in Berkeley and still in the US, then I moved to Bristol, where I've been since 2000. Well, I graduated in 2007, and I've been then in Bristol since now. And I was actually extremely lucky because when I was hired by the University of Bristol, they had two positions. And in the second position, they hired another mathematician, also in dynamical systems. And we met at the job interview. We were both hired, and then, well, today we are husband and wife. So it worked out really well because we never had the two-body problem, and I think we were really, really lucky. And yeah, and well, that's the new addition to the family. So this is Victor, our son, and he's now actually 1 year old. He turned 1, and he started walking. And yeah, and well, so far, my new challenge is indeed to find a good family-work balance, and I don't have answers. It's a process which is just starting. This is my main challenge right now. And well, so far I had 9 months maternity leave, and since January I'm back full-time, and Victor is in nursery, and he seems very happy and enjoying himself. So now, I don't know, now we'll see. So in a few years, you should ask me again how this is going and how is it working out. But yeah. But I'm very happy. I want to do mathematics. I like what I do. I love to be back, and I love Victor, of course. So I hope I can try to find a good balance between the two. Okay, back to mathematics now. And so the title, as you see, so I want to tell you what are polygonal billiards. We'll see today some finite and some infinite ones. And I want to explain how they are connected to surfaces and periodic surfaces in the case of the infinite ones. So what is a billiard? So take a billiard table, for example, a rectangle, and take a ball, which is like without mass, it's a point, and try to shoot this ball in a certain direction. And what happens? So imagine there is no friction, so you move in a straight line until you hit the boundary of your table, and then you are reflected elastically. So the angle of incidence is the same as the angle of reflection. And you keep going. So we are in an ideal billiard without friction, and the particle will keep going unless you hit the pocket. But we are not playing billiard, we are mathematicians, so we actually don't want to send balls in the pocket. We are going to look only at trajectories which never hit the pocket. So billiard trajectories which will keep going on forever. Okay? And Okay, there's no reason, it's boring to play in a rectangle, so you can play billiard in any planar domain, and those are all bounded examples. Today we will restrict ourselves to polygonal type of billiard tables. And that's an example of a picture that I always show. It's by Mundushin. You can play also on more interesting tables in real life, like L-shaped. No, this is actually more of a joke. Okay, why do we study mathematical billiards? So, well, the motivation comes from problems in mathematical physics. And, oh, sorry. Okay, so this is a billiard that I will tell you a lot about towards the end of the talk. And this is an actually infinite planar billiard. So here the billiard table is the complement. You have scatterers, which are squares placed regularly along Z2 vertices. And the billiard table is the complement. So you shoot your trajectory outside, and this is bounced by your scatterers. Okay? So this is an infinite planar polygonal billiard. And this actually was introduced by a couple. So Paul and Tatiana Ehrenfest in 1912. And Tatiana Ehrenfest was a woman mathematician, so it's good to mention her. And while the husband was a physicist. And for them, it was a model for the laws of thermodynamics, and they did. But this is actually, the periodic version is due to Weber. So they were looking at a random array of scatterers. And so even though it was introduced quite early, and there were many people who did numerical simulations on the Ehrenfest billiard, not much was known rigorously until very recent years. And at the end of the talk, I will tell you what are the new developments on the Ehrenfest Win3 model, it's called. Okay. And another example, this is less obvious. So this is a simple system which is made by two masses on a rod with two walls. And imagine that there are elastic reflections among the masses and the walls. And it's an exercise by writing the law of conservation of energy and momentum, but it's not obvious, that you can actually reduce the phase space of this system can be represented by a triangular billiard table, and the motion of the system is given by a billiard trajectory in a triangle. And that's not obvious, but it's not hard to show that, yeah, the system is represented by a billiard in a triangle. So that's another example of, this is already a billiard, but this is an example of a physical system which can be described by a billiard trajectory. Okay? Okay. So billiards are dynamical systems. So you have a deterministic law of evolution that tells you what to do. But usually the behavior of a system can be very complicated and chaotic. So the challenge in dynamics is to describe the long-term evolution of your system. And let me ask you some sample basic questions you can ask for any dynamical system. For example, are there periodic trajectories? So in the billiard, that's an example of a periodic trajectory, a trajectory which closes up. And at the opposite, are there trajectories which are dense? For example, in this picture, this is a finite piece of a trajectory which looks like it's becoming dense, which means it's just getting arbitrarily close to any point on your billiard table. And if the trajectory is dense, you can ask more, is it equidistributed? Which intuitively means, does it spend an equal amount of time in any region of your table? And that's an example where it's less clear that this trajectory is equidistributed because it looks like it's spending a lot of time bouncing in the center. Okay? Okay, and now let's look at infinite systems, infinite billiards. Let me ask you more questions. I'll address these questions at the end of the talk again. So in this case, you can ask, for example, you could also ask, but in the other cases, you can ask whether there are orbits are recurrent. So imagine you shoot your trajectory. Will you come back arbitrarily close to where you started infinitely often? If you come back infinitely often close to where you started, you say that your trajectory is recurrent. Okay? And conversely, are there trajectories which diverge? So they go to infinity and never come back. And are there trajectories which are dense? Again, in this Ehrenfest model, are there dense trajectories? This we already asked. And another question you could ask is, what is the diffusion rate, which means you have your trajectory, it's moving away at some point. What is the largest distance that you reach in time t? So how far from the origin in time t you get? What is the speed of diffusion? Okay, lots of questions. I'll get back to some of these answers. And as I said, for today, I will focus only on billiards in polygons. So I will not look at other type of shapes of tables. And I will make a further restriction, which is that the billiards are so-called rational polygons. That means that all the angles in your polygon are rational multiples of pi. Okay? For example, in this case, they are all pi over 2 or 3 pi over 2. Okay? And I'll tell you more about that. So rational billiards are nowadays very well understood, and that's because there is this beautiful connection with the Muller dynamics that I will mention and say something about later. And that's been, rational billiards have been an active area of research for the past 30 years or more. And just in the past 2-3 years, people have started looking at infinite polygonal billiards, which are periodic, like the Ehrenfest model. And there's lots of new developments in this area, and still using Muller dynamics. And on the other hand, if you consider irrational polygons, so the angles are any angles, then very little is known. So we are very ignorant about. So that's kind of the status of the area. Okay. So, okay, what is the key idea when you want to study a rational billiard? There is a very nice geometric reduction from billiards to flows on surfaces, and that's what I want to explain. So the idea is the following. It's the trajectory gets complicated because you are reflecting the trajectory at the boundary. So why not, let's do something else. Instead of reflecting the trajectory, let's reflect the billiard table. What do I mean? So this is my real trajectory, which has a reflection, and I want to instead keep going straight out of my billiard table and draw a reflected copy of the billiard table. So I'm reflecting the billiard and keeping my trajectory straight. And I can keep doing this. So this is my real trajectory, and this is my straightened trajectory, which is moving through a series of copies which are obtained by reflecting. So I reflect, 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 and reflect. So that procedure is called unfolding of the billiard trajectory. And in this case, clearly you could just get a straight line in a square grid. So your billiard in a square has been unfolded to a straight line in a square grid. But in reality, I don't want to take the whole grid. I can notice that I really need to take only 4 copies, because the order of the reflection group is actually 4. So after 4 reflections, the copy that I get has the same orientation than the initial copy. So I'm going to select these 4 copies as my 4 basic ones. So for example, the black one on top, it's the same than the beginning. So that piece of trajectory, I can just bring it back to the original copy. And this blue, for convenience, I want to actually cut it and paste it over there. So these are my 4 copies. And what does the trajectory do in these 4 copies? What happens? It happens that when you get to the boundary of these 4 copies, you continue in you kind of glue this vertical side with the opposite vertical side. And when the trajectory goes out, you come back to the same point in the opposite side. And similarly, you want to glue the bottom to the top. So when your trajectory hits the top side, it continues through, starting from the same point of the horizontal side. Does it make sense? Okay. So what are we doing? Well, if you take 4 copies of a square and glue, you have a big square, and you glue the opposite parallel sides, well, you are getting a torus. Topologically, that's a torus. And your linear trajectory is actually a trajectory of a linear flow on a torus. Okay? So what did we do? We started from a billiard trajectory, and we got a linear trajectory of a flow on a torus. Okay? And the billiard in the square can be understood in terms of linear flows onto Rhi. And for example, here you can say whether your trajectory is dense or periodic very easily, because according to the slope of your trajectory, well, okay, you can decide if the slope is rational, you'll have a closed trajectory. If it's irrational, you have a dense trajectory. Okay, so it's a useful reduction. And when can we do it? It turns out that you can do the same, well, the same type of unfolding for any rational billiard. So if you have a billiard whose angles are all multiples of rational multiples of pi, for example, this triangle, which has a right angle and an angle pi over 8, then you can do the unfolding and get the surface. How? Let's do this example, one more example, which is a little bit harder than the square. So I'm going to unfold the trajectory, in a billiard trajectory in this triangle. So in this picture, there is the real trajectory, and here I have the unfolded trajectory. So again, at each reflection, I go straight and reflect my billiard table. And how many copies will I need? Well, it turns out that because these angles are rational, I just need finitely many copies. And how many is the order of the reflection group generated by reflections at size. And those are 16 copies. So those are 16 copies of the original billiard table arranged to form a regular octagon. And so this is my unfolded trajectory. And as before, when my trajectory goes out to one of the sides, well, in theory, I should reflect again and get a new copy. But the copy that I obtained by reflecting again, I already have it somewhere else. So when I go out, in reality, I just need to go back to this copy, which is, so I need to glue opposite sides of this octagon, like the gluing, like the color. So the side D needs to be glued to the side D, the side A needs to be glued to A. And my trajectory, when it goes out through one side, it comes back to the opposite parallel side, okay? Okay, so topology exercise, what is this? Well, I claim it's a surface of genus 2, and I'm going also to convince you. So an octagon, you can think of it as a square with 4 corners which were cut out, right? So if I glue the square, we already know that we get a torus. Now, what happens of these 4 corners? These 4 corners, when you glue the square, they form a rhombus on the, and this is actually a hole because these 4 corners were cut. So what I have is a torus with a hole, which is a rhombus hole. And now I still have to glue the B side and the D side, which are the boundaries of this hole. So I glue B. I still have 2 holes that are bounded by D's. And now I deform them and glue them, and I get a surface of genus 2. But, I'm convinced that this is a surface of genus 2. And it's actually a flat surface because it locally has a Euclidean structure, which comes from the fact that I glued it from a piece of plane, right, from a polygon in the plane. And on this flat surface, also called the translation, on any surface which is obtained by gluing polygons by parallel identifications of sides, you have actually an additional structure. You have a notion of linear flow. So on this polygon, I already told you what are linear trajectories. So you just move along a straight line. You pick a direction, and you move along a straight line. And this notion of line, which is well defined in the plane, it's actually also well defined on the surface, because everything is glued by parallel translations. So the notion of direction makes sense also on the surface. There's only a little problem, which is, what is the line? So first of all, the vertices of this octagon turns out to be glued to a unique point on the surface. And that point is a little bit special for the surface, because for that point, actually, there's not a well-defined notion of line through that point, because there are indeed, these are 6 semi-lines which enter that point. So linear trajectories on the surface, the trajectories which never hit the vertices are well-defined trajectories on the surface, and the trajectories which hit the vertex actually are separatrices of a saddle. So this point, it's a saddle singularity for the surface flow. Okay? So in the torus, we didn't have this problem because of Euler characteristic. In higher genus, we have this problem. So we have a linear flow on the surface, which is well-defined outside a finite number of saddle-type singularities. Okay? And again, the linear flow is just moving along trajectories. So for time t, you just flow with unit speed along the line in direction theta. And again, this flow is not defined at the singularities, which are saddles. Okay? Okay. So summary so far, we started from billiards in rational polygons, and by doing unfolding, we showed that a billiard trajectory in a rational polygon can be converted into a trajectory of a linear flow on a translation surface. Okay? Any questions so far? Okay. So now let's start doing dynamics. So a little remark that this flow, it preserves the area. So there is a notion of area in the plane, and areas of sets are preserved when you flow them linearly. And so one of the important properties that people study in dynamics is ergodicity, that I'm going to define. So we say that this flow is ergodic if it doesn't have any trivial invariant sets. So what does this mean? Imagine that you have a set which is invariant under your flow. So phi t of A is equal to A. Then this set either has area 0 or the complement has area 0. So in some sense, the sets which are invariant under the flow are trivial from the point of view of your measure, of your area. So there's no trivial way of decomposing your dynamical system. Okay, so a classical theorem now, this is a theorem of the 80s, which was proven by Kerckhoff, Mason, and Smiley, is the following. So take any translation surface, any surface glued by polygons by parallel translations, and look at the linear flow on this surface. For a random direction, so for almost every direction theta, this linear flow is going to be ergodic. That's a big theorem, which is proven using Teimuller dynamics, and I'll say something at the end of this proof. And the corollary of this theorem is the following. So take a rational polygon, a billiard in a rational polygon. Because this billiard can be unfolded to a linear flow on a translation surface, you know that this is ergodic. And in particular, as a corollary, you know that if you shoot your billiard trajectory in a random direction, this billiard trajectory will be dense. So it will be dense, okay? Sorry, I didn't say. I stated the theorem that it's ergodic, but you can actually prove a little bit stronger result, that it's uniquely ergodic. And let me not define what uniquely ergodic means. But uniquely ergodic actually means that not only it's dense, but your trajectory is going to be uniformly distributed. Okay? So a typical trajectory in a rational billiard is dense and uniformly distributed, thanks to Kerckhoff, Mason, and Smiley. Okay. So the next slide is a little bit of an extra, but I want to mention something related to this that I did in my own work. So there is a stronger property than ergodicity, which is called mixing. Mixing implies ergodicity. And mixing means that sets becomes equidistributing, meaning take a set A and start flowing it for time t. If your system is mixing, then the set A will become equidistributed. And specifically, if you take a target set B somewhere else, after time t, this is an image, a pictorial image. A will kind of equidistribute, and the proportion of A which intersects B will tend to the product of the measure of area of A and area of B. So here I'm imagining that I have a system which preserves the area. So a flow on a surface which preserves area. So if it's mixing, you have this I don't want to. So linear flows turn out not to be mixing. So they are ergodic, but they are not mixing. But there are another class of area-preserving flows on surfaces, which are called locally Hamiltonian flows. So that they come from, again, mathematical physics. And I don't want to define them, but I'm just going to say that they are kind of brothers or sisters, I don't know, of the linear flows, because actually the building blocks of these locally Hamiltonian flows have exactly the same trajectories of the linear flows, but they are so-called time changes. So they are flows which have exactly the same trajectories, but the way you move along a trajectory is different. So instead of moving with unit speed, you move with a different time parameterization, which is given to you by Hamilton equations. So, okay, they're related flows. And for those flows, there was a conjecture open and asked by Arnold whether these related flows are mixing. And a lot of my past work, actually starting from my PhD thesis and in a series of papers, I actually worked answering this conjecture of Arnold and giving a full classification on when they are mixing, on when they are not, and whether they are weakly mixing. And I'm not going to state. This is a little bit of an aside. So, okay. So now I want to move to the infinite world. So what about infinite billiards? I want to move to the Ehrenfest model. Well, for infinite billiards, you can also, rational infinite billiards, you can also do unfolding. So let's try to do unfolding on the Ehrenfest model. So here again, you might remark that actually each trajectory has only 4 possible directions. So green is like down and up, yellow is up. So the colors, each color represents a possible direction, oriented direction. Okay. So I'm going to take 4 copies of the billiard table, obtained by reflecting the billiard table, right? And I'm going to, in each copy, I'm going to just keep the trajectories in one of the directions. So let's see, here I'm keeping the pieces which are green. Here I'm keeping the pieces which are yellow. And if I do it this way, what I'm keeping, they all have the same direction. So I reflected the table in such a way that the trajectories all have the same orientation. Okay? And now imagine you can do some gluings of sides of these squares. For example, when I go up, when I go here, I'm going to glue this side with that side. So when my trajectory goes up here, it comes out in the yellow. Then when it hits here, it comes back over there, and so on. And so you get some infinite translation surface in this way by identifying the sides of these squares. And what is it? Well, there's an easier way to think of it. So this billiard is periodic. So we have this Z2 periodicity. So let's just look at the fundamental domain. That's a fundamental cell for the billiard. So my whole billiard is just Z2 periodic copy of this fundamental cell. So it's actually a Z2 cover of that bit. So I can just unfold the fundamental cell. So I have to take 4 copies of this, do the gluings, and then do my topology exercise of computing what I get. And it turns out that you get a surface of genus 5 with the 4 saddles. And then you remember that your original billiard was a Z2 cover of this fundamental cell. So if you unfold the original billiard, you will believe that you will get something which has to be a Z2 periodic cover of this base surface. And that's kind of what it looks topologically. This is actually it's a periodic surface, infinite surface, which is a Z2 cover of this genus 2 surface. So here you kind of cut 2 of the handles and use them to get a periodization. Okay, but it's actually not a topological picture that we get, but it's actually a metric kind of picture. So yeah, that's a remark. And the billiard trajectory that we had here is unfolded to a linear trajectory on this surface. And I have another example where I can draw linear trajectories a little bit better. So this is another example of an infinite translation surface. This is a staircase. So this is an infinite staircase. And again, you need, see there are labels, and I'm sure you can see them. But basically, everything which is opposite and parallel, you want to glue. So this one is glued to the opposite side. This one is glued to the opposite. And I don't know, everything opposite and parallel you want to identify. So topologically, this surface is a Z cover. So it has a Z periodicity. And topologically, it's like a necklace. It's a Z cover of a genus 1 surface. It's a Z cover of a torus. And here you can draw easily the linear trajectories. So, okay, so you just move along a straight line, and when you hit the top, you use the identifications. So you continue the opposite side, then you go to the, that's a long shoot, and then, okay. So that's an example of a linear trajectory on the staircase. So, is this linear flow ergodic? So are there non-trivial invariant sets? Well, this is one of the first examples of infinite translation surfaces which people looked at, because it was one of the easier. And for example, Hooper, Hubert, and Weiss have a paper where they do much more than that. But one of the things that they show is that, this linear flow is actually recurrent and ergodic. So in particular, if you shoot in a random direction, your trajectory will be dense in this infinite staircase. Okay? So compact surfaces, typically you have ergodicity. In this basic example of infinite one, you have ergodicity. So people naively maybe expect it. Maybe we always have ergodicity also for infinite translation surfaces. And now I think this belief, now turns out that it's quite rare to be ergodic in the infinite setup. So one of the results that I recently proved in a joint work with Krzysztof Frączek is that, for example, the Ehrenfest model, and more in general, a whole class of periodic billiards that I don't want to define, are actually not ergodic typically. So what is the statement? Take the standard Ehrenfest, for example, these are squares with 1/2 side, and shoot in a typical direction. So typically the flow will not be transitive, so there will be no trajectories which are dense, and it will not be ergodic. Okay, yeah. So if you shoot in a random direction, typically you will not see something dense. And this is true actually for any, so in theory you have variations of this Ehrenfest where the sides, there are two parameters which are the length of the sides of a rectangular. And this is true for rational sides, and it's also true for almost every choice of the length of the sides of these rectangles. And I'll mention a few more results. Again, there's been really a lot of recent progress on the Ehrenfest model. So our result is one contribution. So other people, there's a group of people in Marseille. So Hubert, Lelièvre, and Trubetskoy, and later Avila Hubert for all sides. They proved that the typical trajectory is actually recurrent. So even though you are not dense, you will still come back infinitely many times close to where you started. If you remember, those are questions that I asked at the beginning. And even though if you shoot in a typical direction, you will come back infinitely many often, there are still exceptional directions, uncountably many, and actually positive house to dimension, whoever knows what it is. There are many trajectories which escape. They are divergent, so they escape at infinity. And then, you remember, I asked, what is the speed on which you go to infinity? So that's actually an interesting result. So you can look at the distance. Take a point P, look at the billiard trajectory, and look at the distance from the original point after time t. So it turns out that this distance has a polynomial. So this distance will go up and down. It will fluctuate. So you want to look at the lim sup. So what is the farthest you can get in time t. And this lim sup behave like t to the power 2/3. Okay? And that's actually quite curious that many people did numerical simulations on this thing. And I think that the best thing that they were guessing was, I don't know, 0.6. And they were saying, oh, first they thought it's 1/2, then they thought, oh, it's 0.6. And unfortunately, computer simulations in this thing are not very good because it's very slow. Well, okay. So, and this is a rigorous result. So then with Muller dynamics, people found out, oh, it's 2/3. So they were quite far from guessing 2/3 numerically. Okay, a few last slides on what are the techniques that people use to prove this type of results, and the connection with this area called Teichmuller dynamics. So what is the idea? So what do people in mathematics often do? So you start from a simple system and you create a more complicated system which helps you to understand the simple one. So, so what do? We have a translation surface. We have this surface, and we construct the space of all translation surfaces of the same genus. So this space MG is just, it's called moduli space of translation surface. And naively, it's just a collection of all translation surfaces in the same genus and type of saddles. And okay, so a point in this space is actually a single translation surface together with the direction. So it's a space of surfaces with chosen directions. And now, in this abstract space, in this abstract moduli space, we define a new dynamical system. We take a point, which is a surface, and we start deforming it. And deforming it will move it around in the moduli space. So what is the deformation? So you do the following. You start stretching your surface horizontally by a factor e to the t, and contracting it vertically by a factor e to the minus t. So the more you move in time, the more you stretch and contract. So what you're actually doing, you are changing your surface by this deformation. Actually, I should have said not vertically. I mean, you stretch in the, contract the flow direction, and which here is vertical, and expand the orthogonal direction. And here it looks like you are getting something different at every time. But you're not really looking at polygons in the plane, but you're looking at surfaces. And in terms of surfaces, you can actually represent a surface in many ways. You could cut it and paste it in different ways. So even if it looks like it's not, you're getting something completely different, in the space of surfaces, you might come back close to where you started. So this family of deformations is called Teichmuller geodesic flow. Fancy name, but this is a very geometric, easy way of describing it. And why do we do that? Well, this Teichmuller geodesic flow is used to do what is called renormalization in dynamics. So the idea that what is the flow doing for you? It's shrinking the direction of your flow. So if you have a very long trajectory on your surface, when you apply the Teichmuller geodesic flow, it will become a short trajectory on a new surface. So the idea is that your flow is doing something like zooming out. So you have a long trajectory, and you're kind of zooming far away and shrinking it to a small trajectory. The price you have to pay to do this zooming out is that you are changing surface. So you're not always on the same surface, but you're looking at a new surface with a shorter trajectory. But that's a very helpful technique in dynamics to do renormalization. And this is the slide before the last. So there is beautiful connection. I mean, I like it a lot. So the magic thing is that this Teichmuller geodesic flow provides lots of information on your original surface flow. So that's the philosophy. You have a linear flow on a surface, and you think of this linear flow on a surface as a point in this abstract space of translation surfaces. And then you apply your Teichmuller geodesic flow, and you look at this Teichmuller geodesic. And if you can say something about the Teichmuller geodesic flow, often the properties of the Teichmuller geodesics imply some dynamical properties for the original flow. So that's the philosophy, okay? So you study this Teichmuller flow, and Teichmuller flow, in some sense, it's easier to understand because it's hyperbolic, well, whatever. No, not really, but okay. So let me give you some examples. I mentioned this result of Kerckhoff and Mesur and Smiley, that in a typical direction, you have ergodicity, right? So this is based on the following criterion for ergodicity. So if you want to know whether your flow is ergodic or not, what do? You take the corresponding Teichmuller geodesic, and if your Teichmuller geodesic happens to be recurrent, so to come back infinitely many times in modular space to the same place, then you know that your flow was ergodic. So this is one example of connection between these two words, right? And that's how you prove ergodicity. You've proved that the Teichmuller geodesic flow has a finite invariant measure, and hence it's recurrent by Poincaré recurrence, and that gives you ergodicity. And you don't have a good renormalization for infinite translation surfaces, unfortunately, but for periodic translation surfaces, you can still use the Teichmuller geodesic flow for the compact main cell. And that's what people have been doing. It's a little bit more sophisticated. And the other example where, I mentioned two results about RFS, non-ergodicity, my work with Franczek, and this diffusion exponent 2/3 by Delacroix, Hubert, and Lelièvre. And both of them use Teichmuller dynamics. And here I'm not going to go explaining what those are, but the key thing are the Lyapunov exponents of the Teichmuller geodesic flow. So if you can compute these Lyapunov exponents, now, for example, positivity of these Lyapunov exponents gives you non-ergodicity. And actually, these 2/3, this magic exponent 2/3 in the diffusion, is one of the Lyapunov exponents of the Teichmuller geodesic flow. So it's a little bit of a black box, but if you want to know more, I'm happy to try to explain later on. So this is a little bit the philosophy, and I think I'm at the end. I'll just finish by saying, again, as I mentioned, that now if you try to take an irrational billiard, we know very little. So let me just leave you with some open questions. Take even a triangle whose angles are not rational anymore. Then it's not known whether there is a closed trajectory in every triangular billiard. And it's not known whether the billiard flow for an irrational triangle is ergodic. And for example, Katok in the 90s has it's not $1 million prize, it's only $10,000. But just to say, well, he offered $10,000 to who can prove that a random triangle has ergodic billiard flow, and I think they're still there. So, okay, so that's the end of the talk. Thank you. Yeah.
Questions? Yes.
So all billiards are planar.
The ones that I'm looking at, yes. No, you could.
Are there results for higher dimensional billiards?
Yeah, of course, people have looked at higher. You can look at higher dimensional billiards, but in the case of this, so what I said today is that rational billiards are nice because they unfold to a finite surface. So there are a few results known about billiards, for example, in polyhedra or in the cube, especially. You can know a lot. The cube is, but in general, if you take even a regular polyhedron like tetrahedron, you cannot do so this. The group of reflection is not finite, so you don't have a finite unfolding which gives you a finite hyperbolic, finite three-dimensional manifold. So in some sense, there is no good renormalization approach to polyhedral billiards. So I think it's also quite widely open. It's maybe a little bit of a magic thing that for planar and rational angles, we get this nice connection with surfaces and Teichmuller dynamics, and that's what's been exploited to do lots of the things that we know. Yeah. Yeah.
I have maybe a silly question. I don't understand your definition of mixing.
Yes.
You said that the intersection of the image of A with B
Yes.
tends to have the same area as the product.
No,
Is it
yeah.
as a fraction of x?
Yeah, first of all, I should have assumed that the area of the surface is 1. I don't know if this is,
that
yeah,
explains.
I didn't say it, but you're not normal. It should be a probability measure. So in this case, the area should be 1.
So,
Yeah, you're right. I think I should have. Yeah, it should be area. The total area is equal to 1. Yes. Otherwise,
then all good.
yeah. Okay. Fine. Yes. Yes.
And in your picture where you were stretching out your original polygon.
Yeah, the Teichmuller flow. Yes. I can go back to that.
So,
Yeah.
what's the resulting, like, so say you did this for a square and you were stretching it into a rhombus or something.
This type of picture is what
Yeah,
you wanted.
then
Yes.
when you do
Yeah.
your identification, is the only
Yes.
thing that's different the speed of the flow?
But in some sense, topologically, you're not changing anything. So you're right. I mean, you see, the identifications are, you can still, so first remark is that when you do this procedure, what was parallel, it's still parallel. So you can still glue by parallel translations, and you still get a translation surface. And topologically, it's the same genus and the same type of saddles. So topologically, it's actually all the surfaces in that MG, in that space, have the same genus and the same type of singularities. So what you're changing is just the metric. So there is a flat metric, and you're kind of deforming the flat metric. So yeah, sometimes it doesn't look like much, but this is not really a topological surface. It's really a translation surface, which is an object which has a Euclidean structure on it. And what you're changing is the Euclidean structure.
Okay.
Does it make sense? Yeah?
So why doesn't it just collapse? I mean, how can this flow be recurrent?
Yeah, that's what I was trying to hint, but you're right. It's the first time that people see this picture, this is the obvious question. This is not recurrent. In reality, it's typically recurrent because what I'm kind of lying, well, I wasn't very precise. So what I said, I just said vaguely, you look at the space of translation surfaces. But in some sense, there is an equivalence relation. By translation, so if you want, when I say the space of translation surfaces, there is an equivalence relation on polygons. Because two polygons can represent the same translation surface. There are many polygonal presentations of the same translation surface. Maybe I'll give you the most basic example. So this square and this parallelogram are actually the same translation surface. So they're not only genus, any parallelogram will give you the same torus, but they are the same flat torus. Because actually you can just cut and paste by parallel translation one into the other. So you can cut here and move this triangle here, and you get this one. So these two are the same. And similarly, you can do cut and paste operations on these deformed polygons, cut and paste by parallel translations.
So you cut and paste to make it not squished.
Exactly. So they look squished, but you can actually. I used to have a picture when I have something like that, but I don't think I can find. No, so this is not my computer, but yeah, I can show you a picture.
I have an idea.
Yeah, that's the answer. Yeah, but it's true. It's a little bit confusing. It doesn't look recurrent at all, but it is for typical points. Yeah.
So what can you say about this moduli space? Is it compact or?
No, it's not compact. And I don't know, actually people have studied lots of properties of the Muller geodesic flow, and they are trying to understand also the geometry of this modular space. And I don't know. So there is, the way to go to infinity is actually to shrink. So if you have a direction where you have what's called a saddle connection, like a diagonal. Imagine that you flow in a direction where there is, when you have a diagonal which is actually shrinking to zero, that's actually really escaping to infinity, so you cannot. So when it's like in the classical moduli space when you are shrinking a curve to pinch your surface. That's a way to escape to infinity. Or like in the space of lattices when you have a lattice with a short vector. I don't know if you know.
Sort of a bubbling phenomenon? Or?
Yeah, but not bubbling. It's really just pinching phenomenon somehow. Yeah, so it's not compact. There is a compactification. The boundary looks. I don't know. There are many things you can say, but still, I think they are quite ignorant. And I think there are some basic conjecture. There's a conjecture by Kuntsiewicz whether the space is a K-pi1. I don't know about fundamental hoops, and those are open. So we know very little of the topology and geometry of the modular space. Yeah.
So how do they relate to the Riemann moduli space of Riemann surface?
Good question. So this is actually it's a bundle over the standard modular space of Riemann surfaces. So first I should have said, maybe if you have a translation surface, this in particular is a Riemann surface, because the translation structure gives you also, gives you also a Riemann structure, but it's an additional information. It's actually, okay, maybe if I can tell you if you know what that means. Equivalently, a translation surface, it's a Riemann surface together with a abelian differential. So it's a pair x omega, where x is a Riemann surface, and omega is something which locally looks like dz or something. Maybe I should say f of z dz, where f is holomorphic. So it's like a datum of a holomorphic one form on top of your Riemann surface. So the modular space of translation surfaces is actually a bundle of abelian differentials over the standard. Is it in? Yeah. Does it make you happy? Yeah. So, yeah. And it's actually okay. We can talk more later if you want.
One more question. Okay, if not, let's thank the speaker again.